So what is photocurrent IP? What is the expression for IP? IP will be equal to Q by H nu into 1 minus R into 1 minus e to the power of minus R by X into P naught. And responsivity we can find out from this. Responsivity will be equal to IP by P naught. Efficiency given by it is number of electron hole pair divided by number of photons incident. So it is IP by Q divided by P by H. Okay, fine. So take down this. If a photodiode, a photodiode is constructed of gallium arsenide. Photodiode. A band gap energy of 1.43 electron volt. What is the cutoff wavelength? What is the cutoff wavelength? Okay, start doing. So what's given? Akash?
Yes, ma'am.
Yeah. So what are the parameters given?
Ma'am, band gap energy.
Yes. So how we are going to find out? What is the expression between, what is the relation between band gap energy and the wavelength? So absorption. So when the electron absorbs the photon, how much should be its energy to jump from valence band to the conduction band? It absorbs the photon. Photon will be having some energy. So electron, it gains energy from the photon. So how much is it required to jump from valence band to the conduction band? Akash?
Ma'am, your voice is breaking, ma'am. There's some disturbance.
Okay, is it clear now?
Yes, ma'am.
Okay. Can you tell me the energy? How much energy it should be having?
H nu.
Gagan?
H nu.
H nu. Okay, one photon energy will be equal to H into nu. H is the Planck's constant and nu is frequency. Okay, so from that you can find out wavelength. So what is the relation between frequency and wavelength? It is that is equal to C by lambda. You know H value and you know C value and EG is given. So only the unknown parameter is lambda. So what is the relation then lambda? So what I told H nu should be equal to band gap energy. So when this photon energy is equal to the band gap energy, then the electron which gains energy from the photon, since that is equal to band gap energy, then it can jump from valence band to the conduction band. So this relation should be satisfied. Okay. When we want to convert from photons to the electron signal, then only it becomes free electrons. We collect those free electrons, then like conversion of incident photon to current. So here H nu is equal to Eg. H into what is new frequency I told. So that will be equal to C by lambda into EG. Okay. So what is finally lambda? Lambda will be equal to H into C divided by EG. So H you will be knowing Planck's constant. What is the H value? Gagan? What is H value? Planck's constant. I think you solved many problems. What is its value? 6 point? Want to know how many are there?
6.62 into 10 power minus 34.
Okay. Okay, fine. So it should be knowing. And what is C value? 3 into 10 to the power of 8 meters per second. And EG value, actually, you have to represent in joules to find out lambda in meter. But what they have given? They have given in electron volt. So you have to convert to joule. What do you need to do? So what they have given 1.43 electron volt multiplied by 1.6 into 10 to the power of minus 19. It will be joules per electron volt. Electron volts gets cancelled and you will get lambda in terms of meter. Okay. So use this relation and use this expression, find out wavelength value and tell me the wavelength value. So H value substitute, C value substitute, EG they have given. Okay, multiplied with this value and tell me the lambda. How much you got?
$887 nanometer.
Yeah. 887. Okay, in terms of 800 only, I got 870 nanometer. Syed, what's your answer? Hello? Syed. Sunlight.
814 nanometer. I'm getting.
814 is less. You're missing some parameters, I think. No. 870. Near to that is fine. Abhilash. Abhilash, what's your answer?
I'm saying 814 nanometer.
Okay, fine. Let it be. You just check it out again. Take the next problem. Given avalanche photodetector. Given avalanche photodetector of a efficiency of 65%. Given avalanche photodiode efficiency of 65% at a wavelength of 900 nanometer. At a wavelength of 900 nanometer. Okay. Suppose 0.5 microwatt of optical power suppose 0.5 microwatt of optical power produces a multiplication current of 10 microamps. 10 microamps. Find multiplication factor. Find multiplication factor. Okay, read the question. Given avalanche photodiode of efficiency of 65%, given avalanche photodiode of efficiency of 65% at a wavelength of 900 nanometer, wavelength is 900 nanometer and efficiency is 65%. 0.5 micro, almost 0.5 microwatts of optical power produces a multiplicative current of 10 microamps. 0.5 microwatts of optical power. That means the incident power is 0.5 microwatts and it produces multiplicative current of 10 microwatts. So find M actually, multiplicative factor or multiplication factor. Find M. So what is the formula for this actually? So what is M value? M is multiplicative factor and that will be equal to IM by IP. So this happens only in avalanche photodiode. So in avalanche photodiode, amplification happens. So how much amplification happens? That is measured by this M factor. That means M multiplied by IP. So that much amplification happens. So in pin diode, that amplification is missing. So we go for avalanche photodiode for this advantage. So now you have to find out M value, how much amplification happens. So they have given IM value. How much is IM value? It is 10 microamps. Okay, multiplicative current. IM value, they have given 10 microamps. So you have to find M. To find M, we should be knowing IP. So to find out IP, you have to use this formula because they have given efficiency. So, and they have given P in also, the input power, that our incident power, efficiency they have given, only the unknown parameter is IP. Find out IP, substitute in this expression and find out M. Okay? Do it and tell me the answer. First you tell me IP value and then you tell me M. Okay, answer your attendance. Abhilash. Abhilash G.
Present, ma'am.
What is the answer?
Present, ma'am.
Abhilash? How much you got? IP value.
I'm still calculating, ma'am.
Okay, what is the expression you have written for IP?
Ma'am,
Abhilash. What is the expression? How are you going to find out? Using which expression you are going to find out IP? Simply just
to Q by H nu.
Huh?
Q by H nu IP. We have to find multiplicative factor, ma'am.
Okay. So what is the expression? Can you repeat the expression?
Q by H nu, ma'am.
Q by
H nu for IP.
IP. I don't know simply why you want classes. So use it only for the attendance if you come to the classes. If not come to the classes, you're going to log into the class. That's it. Akash,
Present, ma'am.
Anant Krishna. Anant Krishna. Krishna, you have shortage of attendance already. Ashutosh Kumar 05. 05. Ashutosh also shortage of attendance. It's below 85. 06. Ashutosh Kumar 06. So, absent. Bhumika.
Present, ma'am.
Bhuvana.
Present, ma'am.
Bhuvana Ivas is also shortage. It's less than 80. So what formula? How much you got, Bhuvana? The previous answer. Wavelength. How much you got? If you don't answer, I will not consider this class presence. Pratik, answering now. Bhumika. So I
Ma'am?
put absent. How much you go? Sorry, not Bhumika. Bhuvana. Sorry, Bhumika. Bhuvana. Going to consider this class.
Yes, ma'am.
How much you got, Bhuvana? Answer the previous question. At least have you solved it? Okay, have you tried? Have you tried
Yes, ma'am. I'm
solving it? How much you got? Hmm? Hi. Absent. one. Chaitra.
present, ma'am.
Gagan.
Present.
Geeta. Geeta MS. Kaveshri.
Present, ma'am.
Okay, Kaveshri, what expression you have taken for IP? Can you tell me the expression?
Ma'am, efficiency into P in into Q by H nu.
Kishore. Kishore. Namita. Nikita.
Ma'am.
Hello. Are you there, Nikita?
Present, ma'am.
Nikita, what is efficiency? How much efficiency given in the problem? Nikita, can you hear me? Hello. I'm not going to consider this class, Nikita. Divorce is on the border. Exact. If I put absent, then it will be below. Pratik B.
Present, ma'am.
Pratik, I can get all the data, details, and what time you logged in and what time you logged out, all the details I can get. Where you were?
Ma'am, it was network problem, ma'am. I was trying to join. I was in my village. Ma'am.
Okay, now you join. Now we'll let it is good. Okay, Pratik. Have I got the answer for this one?
Ma'am, Geeta present, ma'am.
Hello, Pratik. Prithvish. Prithvish, absent, graded below 85, Prithvish. Sirish. Yes, also below 85, Sirish. Sri Gauri. Sri Gauri. Syed. Syed.
Present. Present, ma'am.
Yeah, Syed, you will get questions next problem questions. I'll ask you. Tanmay. Tanmay,
Present, ma'am.
Tejas,
Present, ma'am.
Unnati,
Present, ma'am.
Ejaregowda.
Present, ma'am.
Present, ma'am.
How many times you touched Tanmay? Preeti,
I'm present, ma'am.
okay, Tanmay. Preeti,
Present, ma'am.
okay. Geeta, what is the answer? How much you got for IP? Geeta. Geeta, can you hear me? Okay, fine. How much you got IP current? IP is equal to? Have you solved it?
Ma'am,
Yeah, what is the IP current? How much you got?
ma'am, Geeta present, ma'am.
Geeta, if you are you getting my point? Can you hear me? Can you hear me, Geeta?
Ma'am, ma'am, network issue, ma'am, here.
Okay, then attend next class. So IP is equal to efficiency Q P in divided by H into nu. Okay, so
Yes, ma'am. Yes, ma'am.
how much you got, Geeta? IP value? So efficiency they have given. Q will be knowing 1.6 into 10 to the power of minus 19. Efficiency is 0.65. And then the P they have given it is how much? 0.5. So in how much it is 0.5 microwatts. Okay. Then so here efficiency Q P divided by H into mu. They have given wavelength, not frequency. So this will be equal to Q P H instead of mu. We have to take it as C by lambda. This is H. C into lambda. Okay. So lambda there we can H is the Planck's constant. C will be the 3 to 10 power minus 8 meters per second. If you calculate from this, we will get IP will be equal to 0.235 microamps. So once we know the IP, then we can calculate M value. M is equal to IM by IP. IM will be knowing, that means they have given in the formula, in the problem, 10 micro divided by 0.235 micro. So finally that gives 43. That means, so if you use avalanche photodiode, then it gives 43 times of the normal pin photodiode current. Okay, so that means IP into M. IP we get from normal pin diode. If you multiply it by 43, so 43 times of IP will be the IM value that we are going to get the avalanche photodiode. So what are the noises, different types of noises we discussed at the receiver side, that means at the photodetector side, because of the statistical nature of the light or the photons, okay, of the signal, light signal, we get the noise. So that one we call as the quantum noise and short noise. That is the first noise, short noise. Mohan sir, Mohan sir, Mohan sir. Okay, first one will be the short noise. second one will be the dark current noise. And third one will be the thermal noise. Okay. So these are the different types of noise what we discussed. First one due to the statistical nature of the optical signal, and second one dark current means because of the light ambiency. There will be some light that is falling on the diode. So without photons also there will be some current generation, and that one we call as the noise, and that is named as dark current noise. In this we will be having two types again. One is bulk current noise and another one is surface current noise. And the third one is thermal noise because of the temperature resistive nature in the diode. Some noise exists, that one we call as the thermal noise. So if you want to find out calculations, that means the performance. If you want to evaluate the performance of the photodiode in digital, how we are going to calculate? We are going to calculate bit error rate. It is a digital signal. Okay, if you want to evaluate the performance of the system, then we are going to do bit error calculation, bit error rate calculation. So what do you mean by bit error rate? Bit error rate, it is the ratio of number of bits received, bit error rate, that is equal to, it is the ratio of number of bits wrongly detected by total number of bits received. Okay, so that one we call as the bit error rate. Suppose if I tell bit error rate is equal to -12. So what do you mean by that? How are you going to calculate number of how many bits are wrong in that? If it is 10 to the power of -12. How are you going to tell how many bits are like wrongly detected? You are going to +1 in quiz if you answer this. Injare Gowda. Good, perfect. So here 10 power -12, I told bit error rate is equal to 10 power -12. And how we are going to write? We are going to write 1 divided by 10 to the power of 12. So that is the meaning of 10 power -12. So that means in the numerator number of bits wrongly detected, that is 1, and total number of bits received, that is 10 power 12. So when we received the total number of bits, that is 10 power 12, out of 10 power 12, 1 that is wrongly detected. In the OFC, it will be in the range of 10 power -9 to 10 power -12. If we use the optical fiber, the number of bits wrongly detection, that will be very, very less. That means out of 10, 12 or 10 power 9, only one bit will be wrongly detected. It is very less. So that is why we use optical fiber and all. So if we use wireless communication, there it is more. Okay. So if you use cable, like OFC or some other cables, it is very less. And that too in OFC, it is very less, bit error rate. And bit error rate, if you want to do the calculation, and so some of the binary data. So we are going to do it for the binary data. And we are going to consider these other considerations we have to make to calculate the bit error rate calculations. Unbiased data. Unbiased means there are 2 bits. Okay, bit means there will be 2 combinations, 0 and then 1. So both noise can happen for both. When you are sending 0, that will be received as 1. When you are sending 1, that will be received as 0. That means error that can happen to both 1 and then 0. So it is like unbiased data. We are not giving more preference to either 1 bit or the 0 bit. It is like unbiased. Both will be considered simultaneously. So that is why unbiased data. And noise is additive in nature. Noise is additive. Okay, and then variance of noise. Variance of noise is different for 0 and 1 bit. Okay, so for the 0 combination and then 1 combination, the variance of noise is different, is not same. So these are the considerations we have to make to calculate the bit error rate. So now we'll see what is the bit error rate formula. What is the derivation of that? So these are the density functions, what I have written. Either the threshold, we can take threshold voltage or threshold current. So this is the threshold current what I have considered. And the signal level above this threshold current, we are going to consider as 1. It is like the modulation will be for the digital signal amplitude shift keying. So the optical signal will be present for the 1 level and the optical signal will be absent for the 0 level at the 0 bit transmission. So how we are going to detect there will be a decision maker or the decision circuit. We are going to, that will be having some threshold value, and the signal level, if it is greater than the threshold level, we are considering as 1 bit, and the signal level less than the threshold level, we are going to consider as the 0 bit. So this is the IP current. So what I have shown, that is the IP current, and here I have written the density functions for the 1 bit and then 0 bit. Okay, so these two are the density functions for 1 bit and then 0 bit. That means probability of receiving 1 bit and then 0 bit. So when you see here again, this is the threshold voltage. We can consider either threshold current or threshold voltage. So the 1 bit that falls on this distribution above this threshold value, then we are going to detect as 1 bit. When it falls below this threshold voltage, then we are going to detect that as 0 bit, and these two are the density functions. Okay, when you see this, so this one, that is the detection of 1 bit, it should be above the threshold level, and when you see this, that is 1 only, that detects 1 only, but that 1 bit that has been detected below the threshold level, so that will be considered as 0. Okay, so that is the noise actually. So this is the 0 bit detection. When we see the distribution, it is below the threshold level only, but the distribution that is overlapped with the PY of 1. That means the distribution that is above the threshold level, and that will be detected as 1. Actually 0 bit was transmitted, but that will be received as 1 because of the distributive nature, and that distribution, and because of the noise we are going to get this kind of distribution. So 4 noises I told, sorry, mainly 3 noises: short noise, dark current, and then thermal noise. So short noise that present in 1 bit transmission, and then dark current and then or thermal noise that will be present in 0 bit transmission. Okay, you know that. So we are transmitting 0 bit. When we are transmitting 0 bit, there is no optical signal, nothing, it is 0. But because of some ambient light or because of some thermal uh, variations, there will be some current generation. Of course, when the current generation happens, that might be detected as 1. Okay, so that one we call as noise. Actually, we have to detect 0 because of these two kinds of noises: dark current or thermal noise, that will be detected as 1, and that is noise. And this one, short noise, that presents only for the 1 bit. When we are transmitting 1 bit, because of this short noise, that will be detected as 0. Okay, so when it falls below the threshold voltage. So here when we see this, the variances are different. It's not same. So this density function and this density function, these two variances are different. They are not same. So this is narrower bit compared to this. So when we write the density function, so that is given by, we can write either in terms of current or in terms of voltage, probability of detected current when 0 transmitted. So that will be given by 1 divided by root 2 pi sigma naught. Sigma naught is the standard deviation. So this is the standard density function because these two are in Gaussian variation. E to the power of minus I, instead of this one is ITH, okay, whole square divided by 2 times of sigma naught square. Okay. So here sigma naught square is the variance and sigma naught is the standard deviation. So this is the empirical formula for this kind of distribution. So this formula will be there. And similarly, if you want to do it for I of 1, then it will be given by root 2 pi sigma 1. Standard deviation and then variance will be different, and then mean value also it will be different. 0 for 0 bit transmission, 1 for 1 bit transmission. E to the power of minus ITH I minus I1 whole square divided by 2 sigma 1 square. Okay, so these two are the density functions: probability I of given 0 transmitted, probability of current received for the 1 bit transmitted. So these two are the density functions. And if you want to find out the bit error rate, that means the probability of the wrongly detection bit, probability of any bit detected wrongly, that can be given by bit error rate, and that will be given by probability of 0, 1 into probability of 1 plus probability of 1 given 0 into probability of 0. That means probability of 0, 1 means probability that means detected 0 when 1 was transmitted. Okay, so here actually 1 was transmitted and 0 has been detected. So that happens where in probability of 1 probability of 1 received. Similarly, probability of 1 detected when 0 transmitted multiplied by probability of 0 received. Okay, so here what is probability of 1 and then what is probability of 0? So what is the probability of 1 and then what is the probability of 0? How much it will be? Okay, there are only 2 bits and those are unbiased data, binary data, only 2 combinations. So what is the probability of receiving 1 and what is the probability of receiving 0?
1 by 2.
1 by 2. Yeah, exactly. 0.5 or 1 by 2. So in that probability, that means probability of receiving 1. So in that probability, how many zeros were detected? So that gives me the noise here. Similarly, So what is the probability of 0? So in that probability of 0, in that receiving probability, how many ones are detected? So if I multiply that, that gives the noise. So this is detection of 0 in one value, and here detection of 1 in 0 bit transmission. So here probability of 1, 0, that will be equal to 1 by 2. So we can write 1 by 2, we can take outside P of 0, 1 plus P of 1, 0. Okay. So we know that we have written general expressions. I in terms of 0 given, I in terms of 1 given. So here I'm going to write these are the general density functions. So we are going to write this in terms of P instead of I, 1 detected when 0 transmitted, and similarly 0 detected 1 transmitted. I can write that as probability of 0, 1, 0 detected when 1 transmitted divided by root pi sigma 1, and we have to specify the area. I mean integration, we have to specify the area, e to the power of minus I1 whole square by 2 sigma 1 square into dr. So what is the area? Similarly, I'll write 1 detected in 0 transmission, 1 divided by root 2 pi sigma naught e to the power of minus I naught whole square 2 sigma naught square di. So can you tell me the integration, this limit and then this limit? Actually here what happens? 0 detected when 1 transmitted. Okay, so when we are going to get 0, just look at and tell me. So when it falls in, you tell me the area, when it falls on which range, so that will be detected as 0. Actually 1 has been transmitted, but that falls somewhere. Where? Can you tell the range where that has fallen so that it will be detected as 0? From where to where? That should be below threshold voltage, no? Or below threshold voltage or below threshold current. Okay, so from minus infinity to this threshold current or voltage, we consider that as 0 detection, and this threshold level to plus infinity, we consider that as 1 detection. So 1 has been transmitted, but that falls in this region, in this area, then what we are going to detect? We are going to detect that as 0. So if you want to find out the distribution, 0 detected, 1 transmitted, then it should be in the range of minus infinity to ITH. ITH and VTH both are fine. Both are electrical signals only we are going to consider. Minus infinity to ITH. Similarly, can you tell the range for 1 detected when 0 transmitted? Can you tell its range? Pratik? I haven't submitted assignment yet. Sorry, attendance yet. Pratik, are you there? Fine. Yes, I'll make 0. Sorry, absent. Okay. So it will be from where to where? ITH to infinity. Okay. So when we are going to detect 1, when it is in this range, threshold to infinity. Okay. So when we are going to detect that as 0, when it is in this range, minus infinity to ITH. So that is why in the integration limits we have to give like this. But so this, the problem is it cannot be solved in closed form. Okay, so it cannot be solved in closed form. So what we do, we are going to represent this as error functions. Okay, it's complementary error functions. There are some standard error functions. The error functions table will be like this. Not table, the expression 2 divided by root pi x to infinity e to the power of minus y square dy. So what we do, and for this, if you find out the value of this and error function, tables will be there. From that table, we can get the value. So we are going to put these two values in terms of this error function only. That will be equal to 1 by 2 error function. This is complementary error function. I1 minus ITH by sigma 1 into root 2. Okay. So if you know I1 value, ITH, and then standard deviation to some value, it will be having some tables. From that table, we are going to get value of this complementary error function. So no need to solve. This cannot be solved in the closed form. So we are going to convert in terms of error function, because we can get value from this. So when we are having value from these error functions, so we express these probabilities in terms of error functions only. Complementary error functions. So this is when 0 detected, 1 transmitted. For 1 detected, 0 transmitted, then it will be equal to complementary error function ITH minus I naught divided by sigma naught into root. Okay. So if you substitute all these values, so we got P01 and then conditional probability P01 and then conditional probability for 1 detected, 0 transmitted, then bit error rate will be equal to, so 1 by 2, we can take that outside. It becomes 1 by 4 complementary error function of I1 minus ITH by sigma 1 root 2 plus error function of ITH minus I naught by sigma naught root 2. Okay, just substitute these values in this expression, BR expression. Okay, but that is not final. शायद someone telling. So to optimize it, so what do we do? Actually, what is our intention? We need to decrease BR. Okay, so we need to decrease as much as possible. So here to optimize it, to get minimum BER, so we have to select ITH, the proper threshold value. So to get optimum ITH, we need to equal ITH minus I naught divided by sigma naught. Okay, that means when bit error areas are equal. So when these two are equal, then we can get optimum ITH. So once we find out the threshold value, the optimum threshold value, that decreases the BR. So every time we tell threshold value, the decision circuit, we are going to set threshold value. Depending on the threshold value, we are going to decide whether 0 level or 1 level. So what is threshold level? What is the threshold value? How we are going to decide the threshold value? So for that, this is the equation we use. From this, we can calculate the ITH, and that will be equal to sigma naught I1 plus sigma 1 I naught. Okay, so this is the ITH and this is the optimum value. If we use that, then bit error rate will be minimum. And we are going to represent in terms of Q some parameters I1 minus I naught divided by sigma 1 sigma naught. So finally, if we substitute all these values, then bit error rate will be equal to 1 by 2 error function of Q divided by root. This is the final expression and this is very, very important. This derivation is very important. Got it? Okay, so this is the way of calculating bit error rate. Any doubt in this? So here, once we find out this Q by root 2, then from the error function, complementary error function tables, we can find out this value and that will be equal to the BER value. Okay. Any doubt in this? If you don't have any doubt, I'm going to stop here today. In the next class, I'll take power budget and then rise time budget. Okay, how many are there? Fine. Thank you. We'll meet in the next class.